last test took me 6 hours, so.
All right, any questions?
Can you have negative kinetic energy?
No. Not unless you have a negative mass or an imaginary speed. And to my knowledge, they do not exist. I guess indirectly that was about the master set.
Kind of, yeah.
Any other questions? All right. I'm going to go through, I know I have a video on this, so I'm going to go through it, and then we'll extend on it. Okay.
Oh, black on black.
I have a door that's swinging around at some angular speed. It has a mass M, pivot point here. Let's figure out the kinetic energy.
One half mc squared.
You know, the mixing of colors seems kind of cool, but it makes me wonder if this thing's about to break. Anyway, I miss chalkboards. All right, so mass of the door, that's clear. If I told you what the mass is, that's what you stick in for here. But what do you stick in for the speed? The angular velocity is not speed.
You do angular velocity times the radius.
All right, so I know that V is equal to omega R, so what radius are you gonna pick?
The axial radius. maybe?
That distance right there?
Sure.
Trying to figure out what you mean. That was not
I don't know the
convincing.
word for it. It's like the word. It's like the lever arm.
The hinge?
So, all right, so we have a hinge here. That's a, however wide the door is, overhead view. What radius would you pick? What distance would you pick? The full distance,
there-
or a
is
little
like the-
distance, halfway? What?
Is the force that's compelling the door to move unknown?
Say it again.
Is the force that is compelling the door to move unknown?
The door is just moving.
Okay.
It comes into existence already moving.
I guess just the radius, like the door's length.
Okay. So that would put the speed of the door at, let's say that's 0.5. Omega is 6 radians per, let's make it 12 because just in case we have to use it for something else. 12 radians per second. So you would have the speed at 6 meters per second.
I think so.
If omega is 12 radians per second, and that distance there is a half a meter.
Yeah.
All right. So this point right here, I'll agree, is going 6 meters per second. How fast is this point going?
Is that like 0?
Right there at the hinge.
0.
Okay. So, but doing it this way, you are representing the entire door is going 6 meters per second when that's going 0.
Okay.
So, and I don't have to just pick on Cooper, other people can join. This is your time to stand up and go, Cooper, what were you thinking? The answer is clearly,
Makes me got it.
Is it like the integral of the whole door?
ultimately we're heading there. We will not do the integral, we'll just do an infinite sum. Why would you need to do an infinite sum?
Because there's infinitely many points or radiuses on the door.
Say it again?
Yeah, infinitely many points that you can pick a radius from.
Yeah. we can come up with an approximation. Let's undo that. We can do an approximation by assuming the R is the half point, but it's still not a particularly good estimate. We could cut it in half and treat it as 2 points, and so the kinetic energy would be 1/2 some, we'll call this part 1 and that part 2, m1 v1 squared plus 1/2 m2 v2 squared. But that's still just a crude approximation. And so really, to do it properly, as Mason was hinting, we have to treat this as a whole bunch of infinite little bits of door. So the kinetic energy is 1/2, well, actually, extend on that one, plus dot, 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 and so on. So it's the sum of 1/2 m sub I v sub I squared, where I goes from 1 to however many pieces you break it up into. Ultimately, you're gonna, to do it properly, you would break it up into an infinite number of pieces. But that leaves us with a problem without calculus of how do you add up an infinite number of things. All right, so let's just say from 1 to, yeah, we'll stick infinity in there. Well, every term is going to have 1/2 in it, so we can factor it out. So I've got a 1/2 sticking out front, m sub I and v sub I squared. So every part of that door is potentially traveling at a different speed. So what we do know, assuming it's a rigid door, that they all have the same angular speed. They all will travel through the same angle in the same amount of time. So what I'm going to do is I'm going to make that substitution right there. So I got 1/2 m sub I omega r sub I squared. Omega is the same for everything. So it just stays as omega. I don't need a subscript for it. So I end up with my kinetic energy is equal to 1/2. Well, I have an omega squared that's the same for everything, so I can factor that out. And I'm left with this infinite sum, MIRI squared. And this is so much easier. And then the 10-second calculus aside, this would be 1/2 omega squared integral dm r squared. This bit right here, for those who have seen the video, what is this equal to? Okay. This is the moment of inertia. So yesterday, it was yesterday, when I wrote the formula for rotational kinetic energy, I wrote 1/2 I omega squared. It's basically, I is defined so that this works out.
Why can't you take the mass out? It's gonna have the same mass.
The mass is infinitesimally small, so it's just the nature of the math that it stays in. And since there's no guarantee that the density is the same throughout the door, m sub I is not necessarily the same. All right, so you're left with this situation right here, and so if I have a disk of some thickness, rotating about its center, so disk, rotating about its central point, what would this be equal to? we would, sorry, it has some mass M and an outer radius of R. When you say same thing, you're just saying that.
Yeah, well, with the new mass and the new radius.
Pardon?
With the new mass and the new radius.
Well, still, if we're doing this one, we're breaking it up into an infinite number of pieces, just we have a maximum value of R sub I. All right, yeah, Corey.
Is the disc already in motion?
It doesn't have to be in motion to have a moment of inertia. But if it's not rotating, then moment of inertia doesn't necessarily have much sense there. All right, so we're faced with a situation where it really does not seem particularly obvious how you figure out the moment of inertia with the formula for the moment of inertia of this disk if you're doing an infinite sum. Fortunately, it's already been done for you. For common objects, the formula has already been calculated. For those who've had calculus, there's something sort of neat about deriving it and getting the formula that someone else has gotten. But it's not necessary, especially for 151, which is not calculus based. So if I have a disk rotating about that spot there, so if we have a mass of, let's say it's a 2 kilogram disk, and R is 0.3 meters, so the diameter is about like that, mass is 2 kilograms. Then the moment of inertia, if it's spinning about the central point, plug and chug, 1/2 times 2 kilograms times 0.3 meters squared, and we end up with 0.09 units.
Kilogram meters
Oh, you're stopping there?
squared.
There we go. Kilogram meter squared. There is no one word unit for it. All right, so all that is, sure, I know, it's exciting, but wait, it gets even more exciting. So if, suppose I have a long, thin rod, rotating about its central axis. So rotating about the center of mass, probably better wording. Just wondering if I had something set so that it would do multiple colors, but, yeah. All right, you can look this up, you can derive it, you can look it up, and it is 1/3, oops, sorry, 1/12 ml squared. Trust me. Or look it up and tell me I'm wrong. But if I've got a rod rotating about the end point, so this is the thin rod, and thin rod is defined as this distance right here is significantly less than the length. If you need a better rule of thumb, this distance is less than 10% of the total length. But if it's rotating about the end, how do we deal with it? Well, some places you can look this one up, but you can also derive it. First off, well, let's go ahead and do some numbers here. So if I have a mass of, why don't we stick with 2 kilograms, and a length of 0.3 meters, and a width of 0.01 meters. What is the moment of inertia? who don't have a calculator, we could also express the answer as a fraction.
Point 015 kilogram meter squared.
All right. So if I move my pivot point to here, will the moment of inertia go up or go down?
Oh,
Why?
is it the same rod?
Yep.
Because there's a longer radius.
Okay. Looking at it just slightly differently, this part right here, it would be this part would have the same moment of inertia as this part would, or this part, either of them. But this is farther away from the axis, and since we have mr squared, since the radius is squared, it's gonna have a much bigger impact. So yes, indeed, it will go up. But the length is the same, mass is the same. What is different is this number right here. So if you know the formula for it's rotating about its center of mass, but it's not rotating about its center of mass, then you have to use, instead of the axis being here, it is parallel, and over here, you have to use the parallel axis theorem. Not quite sure why they call it a theorem, because it's all based on definitions. The parallel axis theorem is that the moment of inertia rotating about some point P, or some axis P, is the moment of inertia rotating about its center of mass, plus mh squared, where h is the distance from C to P. So we are moving the axis from here to here, so we've moved it half the length. So the moment of inertia about this point here, so that's point P, and center of mass is point C. That moment of inertia would be the 1/12 ml squared. That's the moment of inertia about the center of mass, on sub C, plus m times half the length squared. Because we moved the axis half the length. So this becomes 1/12 ml squared plus 1/4 ml squared, which is 1/3 ml squared. So from this, we don't have, we now basically have opened it up to a whole bunch of things. So we just need to know a couple basic shapes, or if you don't know it, you look on the first page of the test, or you find it in every beginning textbook in physics.
So is 1/12 ml squared always the moment of inertia when you have it rotating around the center of mass?
For a thin rod.
Is that derived from 1/2 mr squared?
No, it's not derived from that, it's derived.
So it's two different equations.
Yes.
Okay, and then how do we get h?
H is the distance that you move the axis. So you have the center here, that's where we originally have the formula for it. And instead of rotating about that point, we're gonna have it rotate about the end.
Okay.
So H is the distance that it moves. It is the distance between the parallel axes.
Oh, I'm sorry, I see L over 2, I thought it was 1/2, that's why I was confused.
Oh, no, that's an L.
Yeah. That makes sense.
Okay.
What would you do if the point wasn't at the end, it was like just slightly below the center?
You would still use the parallel axis theorem.
You just wouldn't use L over 2, you just use something different.
Right. So the L over, when you go to the basic chart of basic shapes, some of them will have both of these, some of them will just have this one. But this is sometimes considered basic enough. So, but if you went to some, like right there, that's not gonna be in any basic table. So you'd have to use parallel axis theorem.
Would you just like approximate if it didn't tell you what the exact measurement was?
Yeah, you should be given the exact measurement if you have to calculate it. Notice also that by moving the axis from here to the end, we basically quadrupled the moment of inertia. So, this moment of inertia, like 0.060. All right, so we've, actually, let me go grab a prop. I'm just gonna let the camera roll. We'll be right back.
Thursday's like Christmas. I'm snoozing so hard in the car, but it's slashed. Like, I woke up right after this.
It just seems so arbitrary.
I turned mine in today.
All right, so I have two objects here.
Lightsabers.
Sure.
Can we beat people with them?
They have the exact same mass, exact same length. The difference is the mass distribution. This one has mass, see where it's sort of the blacked out window there. This has mass out here, and here where you can see through it. No mass. That's Roberto Duran would say. And here, the mass is here instead of out here. So, but they have the same total mass, just the red one, the mass is concentrated towards the center, the blue one towards the outside. So first off, which one has a greater center